Start.
IIT Bombay Master Rover project is a student technical initiative to build rover prototype setup capable of all-terrain rover traversal, performing consist tasks using robotic arm and conducting on-board tests for passenger identification.
Improving upon our previous iteration's performance, we designed this year's suspension. It consists of a traditional 6-wheel rocker bogie system along with a 4-bar linkage mechanism connecting both rockers. The legs are made up of hollow aluminum tubes, making the design light at around 7 kilos. The current suspension system provides better stability on rough surfaces, has higher obstacle climbing capacity, lesser wheel pressure and power requirements in comparison to our previous 4-wheeled iteration. The Rover uses skid steering mechanism for terrain traversal, which was preferred over explicit steering due to its smaller turn radius requirement and simplicity in its implementation.
Current design, a custom-built aluminum wheel hub has been made. The rim is rolled using a sheet metal bending process and welded with the hub. The wheel is coated with rubber sheets with rubber strips stuck on the top of that to give groovings. This improves its traction over uneven terrain.
For the robotic arm, we have opted for a 6 degree of freedom assembly. Rigorous simulations of the arm components were done using ANSYS static, structural and transient simulation, which let us choose the best materials keeping in mind the rover's weight, overall strength and durability. Wrist joints and gripper mechanism uses rotary actuators for increased precision and control. Along with that, we have chosen a 2-fingered gripper with a lead screw mechanism as they do not require a braking system to eliminate the back driving. Linear actuators drive the elbow and shoulder links for increased stability and load distribution. In this iteration, the links are hollow cylindrical instead of a truss system for an even stress distribution throughout the component.
Subsystem, we design live detection equipment and check if there is extent of flow like present within the.
The robotic arm equipped with digger claws is used to collect the soil sample from the ground and transfer it to the inclined plane at the other edge of the chassis. A servo rotates 2 cuvettes to analyze 2 soil samples independently. Based on the Raman effect, the spectrometer detects the constituent elements of the soil sample using a laser along with a combination of mirrors and grating. An actuator and servo operates to drop soil sample and reagent on the slide. XCT and saffron dye tests are performed for analysis. A 6 degrees of freedom steward platform helps to drain excess water and focus the image for a microscope. 3 biosensors are used to measure humidity, temperature and methane in the surrounding. An inclined plane and a servo is used to test 2 samples independently. A pump transfers water to the funnel which is mixed with the sample and then distributed to microscope and spectrometer.
From past experiences, this year the hardware subsystem has focused on improving system reliability and ensuring easy, quick and smooth setup of the rover and base station.
We have an Intel NUC as the main onboard computer powered by an independent power supply to protect it from the load-related voltage fluctuations produced by the Roboclaw motor drivers. The entire system has been schemed out neatly in a closed elect box with various connectors to enable easy rover setup and a power isolating kill switch. For the base station, we have a simple root configured ruckus module as a master communication node and a Logitech joystick configured to provide full rover drive and arm control. The Ruckus P300 module boasts of a 1 km non-line of sight range, which has been verified via multiple field trials. To avoid a complete communication blackout, we have used a time series prediction algorithm to predict signal strength based on Ruckus RSSI values.
The Autonomous and Image Processing Subdivision have focused on achieving the assigned task by the use of AR tag detection algorithm integrated with level 3 autonomy for the traversal of rover.
The stereo depth cam Intel Real Sense is mounted on the rover to give us the IMU data in point cloud format. The camera feed obtained is used to detect AR tags using image thresholding and contour detection. The path planning algorithm has a global planner that uses Dijkstra algorithm and the local planner that uses DWA. Both the planners have an occupancy grid created by the cartographer which also maps the rover environment, making it a robust SLAM algorithm. The rover traverses at the given GPS coordinates autonomously. It then detects any AR post nearby. This puts the LiDAR in action to verify the exact location of the coordinates to move into. It flashes green on passing through the post for indicating a success.
In the upcoming month, we plan on refining our design based on the results of our field testing. With this, we conclude the submission for URC 2022.